Welcome back. Today we will see how floating point numbers are represented in a computer program. Previously we saw how integers are represented in base 2. Now let's see how floating point numbers are represented in base 2 with what's known as the normalized scientific notation. So a number represented in the normalized scientific form in base 2 will look like minus 1 to the power of s times m times 2 to the power of e, wherein s is sign, m is the mantis or the fractional part, and e is the exponent. So for example, 0.1 in the normalized scientific form will look like minus 1 to the power of 0 times 1.6 times 2 to the power of minus 4. Now you may be wondering why 1.6 times 2 to the power of minus 4? Why not 0.1 times 2 to the power of 0, or 0.2 times 2 to the power of minus 1, or 0.8 times 2 to the power of minus 3? Notice all of them equate to 0.1, but none of them are in the normalized form. So what normalized here means is that the number behind the decimal point is fixed to be equal to 1. So the only place where this happens is when it is 1.6 times 2 to the power of minus 4. So again, none of these are in normalized form. Now there are two types of floating point numbers in C++. The first is 32-bit single precision float. Now notice that 32 bits are divided into three groups. The first group is 1-bit sign. The next 8 bits represent the exponent. The last 23 bit represent the fractional part of the mantissa. So since the fractional part or the mantissa is 23 bit, plus we have one fixed bit which we don't have to store because it's always equal to 1, the precision here is 24 bits. Now converting that into decimal, we see that the accuracy is 7 significant digits. Now what this means is that any floating point number represented using a 32-bit single precision float will be accurate only up to 7 decimal digits. Beyond that, we will only have an approximation. Now the range of a 32-bit single precision float goes from minus 33.4 times 10 to the power of 38 to plus 3.4 times 10 to the power of 38. Notice this is much larger than what we saw with integers. Now let's go back to the example of 0.1. Let's look at how 0.1 is represented in a 32-bit single precision float. Now the first bit here is the sign bit, so the sign was 0. The next 8 bits encode the exponent. So the 8 bits will store what is the offset of the exponent to 127. Here the offset of the exponent to 127 is 123. So 123 minus 127 is equal to minus 4. And therefore 123 is represented in binary in the next 8 bits. Now the remaining 23 bits encode 0.6. Now notice 0.6 has a repeating pattern. That is 1001 is repeated 5 times. So we have 1001 followed by 1001, 1001, 1001, 1001. And the last one, instead of being 100, is rounded to 101. The reason why the last bit is flipped from 0 to 1 is because we need to round this number to represent it as accurately as possible. Now the number that is stored as a float is 0.1 with 0000000 and then few other digits. We see after 7 significant digits, they're not anymore accurate. Now the other floating point type in C++ is 64-bit double precision float, which has one sign bit, 11 exponent bits, and 52-bit mantissa. So now the range is much larger than 32-bit single precision. The range is from minus 1.7 times 10 to the power of 308 to plus 1.7 times 10 to the power of 308. And now notice also the accuracy is higher. 64-bit double precision floats are accurate up to 16 significant digits. Now the reason this is because we have a 52-bit mantissa plus one fixed bit, so the precision is 53 bits. And converting that from binary to decimal, we see that it is accurate up to 16 decimal digits. Now if you have floating point numbers that are bigger than 7 decimal digits, you need to use 64-bit double precision floats to accurately represent them in computer programs. However, the downside is 64-bit double precision float needs twice the memory than 32-bit single precision floats. So if you need to store a large number of floating point numbers, the memory will come into play. Now let's look at density of 32-bit floats. Previously we saw that the 32-bit float has 23-bit mantissa. So what this means is, for a fixed exponent, the number of different fractions that we can represent is 2 to the power of 23. Now notice we have 23 bits of fractional part. Each bit can take value which is 0 or 1. So the total number of different fractions is 2 to the power of 23. In decimal, it is approximately equal to 8 times 10 to the power of 6. Now what this means is, when e is equal to 0, the number of floats between 1 and 2 is approximately 8 into 10 to the power of 6, which is quite a lot. Now let's see what happens similarly when e is equal to 1. When e is equal to 1, the floating point numbers that we can represent are between 2 and 4. And we still have 8 into 10 to the power of 6 floats to represent all the floats between 2 and 4. Similarly, between 4 and 8, we still have 8 into 10 to the power of 6 floats to represent them. But this also applies when the exponents are higher. That is, when e is equal to 23 or 24, the number of floats between 2 to the power of 24 minus 2 to the power of 25 is still 8 into 10 to the power of 6. So again, we have fixed number of floats even at lower and higher exponents. However, notice 2 to the power of 24 minus 2 to the power of 23 is approximately 8 into 10 to the power of 6, and 2 to the power of 25 minus 2 to the power of 24 is approximately 2 times 8 into 10 to the power of 6. Now what this means is, we have more numbers to represent than the numbers that can be represented. So we have approximately 2 times 8 into 10 to the power of 6 integers between 2 to the power of 24 and 2 to the power of 25. However, we can only represent 8 into 10 to the power of 6 floats using 32-bit single precision floats. Now this is a problem. What this means is, not all integers greater than 2 to the power of 24 can be represented exactly using floats. This also means that not all floating point numbers greater than 2 to the power of 24 can be exactly represented using floats. So when you have, again, numbers which have more than 8 significant digits, or a number greater than 2 to the power of 24, you need to use 64-bit double precision floats to not have any errors in the number, the way the number is stored in a computer program. Now let's look at the major differences between floats in C++ and real numbers. We know real numbers have infinite range in precision, but this is also true for floating point numbers in C++. So let's look at that. So the floating point numbers in C++ have finite precision and range. We already looked at this before. The finite precision is because we have a fixed number of bits for the mantissa. In case of 32-bit floats, we have 24-bit as the precision. In case of 64-bit double precision floats, we have 53-bit precision. Now the range is again finite, and this is because we have again fixed number of bits for the exponent. Now let's look at other differences. We know that real numbers are commutative. That is, when we add two real numbers, a plus b, it is also equal to b plus a. But is this true for floating point numbers in C++? It is true for floating point in C++ also. However, floating point numbers in C++ are not necessarily associative and distributive. We know that real numbers are both associative and distributive, but since we have finite precision and range for floating point numbers in C++, they are not always associative and distributive. This can be surprising initially, but we will see some examples, and through examples it will become clear as to when these properties may fail and what we should do to make sure that we will not encounter such situations in our code. So let's look at some examples in Visual Studio. There are quite a few different things that we want to pay attention to here. The first one is, we know that 0.4 minus 0.3 is equal to 0.1, but when we represent them as 32-bit floats or double, will they be equal to 0.1 or not? That's the question. The second one is whether 0.75 minus 0.25 is equal to 0.5 or not. The next one is, what is 100 million plus 1? And the last one checks whether floating point numbers represented in C++ are associative or not. So let's switch to Visual Studio now, and let's look at some examples.